Um, so my name is Sachin Chitta. I manage the autonomous research group at Willow Garage. My colleague, Yuan Chu Khan. And today we're going to talk about, we're going to give you a little bit of an introduction to ROS and also talk about MoveIt, which is a set of tools that we are building for mobile manipulation applications. So to give you a little bit of background on ROS and sort of the thought process that went behind it, if you look at research robotics, there's a lot of advances definitely happening in that area. But quite often what you see is that there's a reinvention of the wheel. People start doing the same thing over and over again. And that's because they don't have a set of reusable components, or they didn't have a set of reusable components that they could just rely on and build on. And there's a very short lifespan to research results, and that's because most of these things are done by, especially in academia, by graduate students, and they will move on, and the results don't get out into industry, and they're not used as much as they should be. One of the other problems we noticed is that there's an inability to compare results. So you might do a set of experiments with your own robot, and it's very hard to compare it with experiments that somebody else might have done with another robot, because you have to implement everything. You don't have any code that you can share, and that became a huge issue. And ROS was designed to solve these issues. So basically, it's a set of components, it's a set of tools that allows the whole community to share results, to share idea, to share data together. And in industrial robotics, you have a slightly different set of problems. You don't have great development tools, so the development tools have not kept up to pace with the rapid advance in computing and software engineering. You have a limited set of capabilities. Some of the research capabilities, which might actually be mature, have not gotten out as far as they should. And one of the biggest problems is portability and flexibility. Every time you're working with different robots, you might have different interfaces with different sensors. You might have to deal with different drivers, and there's no common infrastructure to pull all these things together. And that's why there's sort of a slow technology adoption. It takes a little bit of time for these things to go through. And that's where ROS-Industrial comes in. And SwRI has done a fantastic job of taking the new results in ROS, the new software that we have, the new technology that we have, and sort of pushing these into the industrial domain and providing a common platform. That I think is the key. There's a common platform that brings all these robots and sensors together, and that way higher level applications start becoming easier to do. So if you think about ROS really consists of what we think of as 4 parts. There's the plumbing, which is at the lowest level. So this is the set of tools. So this is the communication, the build system, things like that, which pull stuff together, and they allow your programs to talk to each other. Then there's a set of tools. So there's things like visualization. There's robot representations. There's introspection into what's going on at different levels of your software stack. There's capabilities, which is things like some of the things I'm going to talk about next. So advanced manipulation capabilities, advanced perception, and how to really pull these all together. So at the higher level as well, stitch them together to build applications. And also, I think one of the biggest strengths of ROS is the ecosystem. So this is a huge network of robotics researchers, industry professionals, students, companies, universities, research labs, which have pulled together and are starting to use these ideas in both their research, and also we're starting to see these in products as well. So there are some companies who base their entire code base on ROS right now. And this ecosystem allows the development of new capabilities, but more importantly, it allows the sharing. So there's a lot of shared knowledge, and if we get this out as fast as we can, then we can build up higher capabilities faster. So this is the second part of my talk, where I'm going to talk about MoveIt. And basically, MoveIt is a set of tools that we built for mobile manipulation applications. And we believe that these are tools that are of real interest to the audience that's here right now. So I'm going to talk about the tools, show you some of the things you can do with it, and talk about how you could harness these tools for your individual applications. So MoveIt really is a set of software. It's basically for building mobile manipulation applications, and it integrates perception, motion planning, kinematics, manipulation, trajectory processing, and execution. And our goal in developing MoveIt was to provide people like you with a set of tools that are easy to configure. So if you have a new robot, if you have your own robot, it should be very easy for you to start using these. They're high performance, so they're good enough and fast enough that you can think of actually putting them into your products. They're developer friendly, so it's easy for people working with these tools to develop new applications, and they're also user friendly. So you can think of using it at a higher level and basically integrating a lot of the things that we've already provided out of the box into your applications. And for those of you who have been using ROS for a while, MoveIt is really an evolution and intended to be a full replacement and beyond for the arm navigation set of tools. So these were our earlier set of software tools that were used for manipulation. And this video actually takes you through all the most of the capabilities that we have in MoveIt. So this is actually built on arm navigation, And essentially it's showing a pick-and-place application using the PR2 robot. And you can see everything from sensing to environment representation. So in this case, the robot is using its onboard 3D sensor to build a full representation of the environment on the fly so that it can do collision avoidance. It's doing perception to recognize the objects of interest in the environment, so it can do grasping. It does grasp planning, so for different types of objects, it either has pre-computed grasps that it can use, or in this case, this is a visualization of how it's actually testing out a bunch of grasps online so that it can know what to do. And there are different ways that we can do all these things, and the key is that all this technology is fully integrated into a set of applications that you can use almost out of the box in MoveIt. So this is a set of robots that have been using our software for quite a while now. On the top in the left, this is actually the Carobot from Fraunhofer IPA, who's leading the European initiative for ROS-Industrial. There's actually in the middle this mobile manipulation robot that you see with the universal arm is also from Fraunhofer IPA. That is the Rob at Work robot. There's a couple of industrial robots that were integrated as part of the ROS-Industrial consortium. On the top in the right, you can see the NASA Robonaut. Oh, thank you. So this is the NASA Robonaut. This actually also now is starting to use MoveIt, and they had integrated the arm navigation and other capabilities on that robot. This is a DARPA robot, a DARPA research program. This is a robot at the Technical University of Munich that is also using arm navigation. This is the NOW robot from the University of Freiburg, who were also using some of our motion planning stacks. And this is another robot project in Europe, which is using our stacks with actually a multi-fingered hand. So there's a real wide variety of robots and a wide variety of applications, especially on the mobile manipulation side, where we've been able to demonstrate significant sophistication in terms of applications and capabilities. So MoveIt is basically a collection of capabilities. And this is a full list of most of the capabilities that we have, but I'll talk through each of these as we go along. Essentially, we start with really fast collision checking. So we have a couple of new collision checking libraries that are fast and pretty flexible. Integrated kinematics, so you can get kinematics capabilities out of the box with MoveIt. You don't really have to do anything extra. Motion planning, fast, good quality paths, which take into account constraints and collisions with the environment. Integrated perception, I think this is actually one of the coolest parts of MoveIt, is you can integrate any 3D sensor that gives you point clouds. We've got standardized interfaces to controllers, execution and monitoring, and kinematic analysis applications, among other things. And I'll show you brief examples of all of these. So I'm going to start off by showing you what MoveIt looks like. So in this case, what we're showing you is a GUI-based interface to MoveIt, which allows you basically to interact directly with a visualized version of the robot. So over here, we're interacting with the PR2. So you can see we can generate motion plans. We can select different arms of the robot on the fly. So you can easily switch between doing things with the left arm to doing things with the right arm. You can import geometry information, so you can import scenes, you can import objects, you can import CAD models directly into the environment. So if you're thinking of using this in a work cell or a workspace where you have a CAD model of the environment, you can do it that way. The inverse kinematics is collision aware. So in this case, you saw that one of the links turned red. That's because for that particular solution, the robot was in collision. The world geometry can be edited. So you can change the scene, directly edit it online through this interface that you want. So basically, this is a set of tools this is actually the ROS visualizer, RViz. So this is a set of tools that are available for you through RViz so that you can directly interact with the robot. And basically, this lets you try out things first in simulation before you go and execute these on the robot. And configuration of robots in MoveIt is very easy. So you just saw a bunch of things that we were able to do with the Pier 2. What you're going to see now in this movie is the same capabilities, but being set up with the modem and arm. And this movie basically walks you through the configuration steps so that you can actually do this on a different robot. So in this case, what we're doing is pre-computing a set of collision operations. So this allows us to make collision operation really fast online by caching some interface. And the tool that we use to do this is called the MoveIt Setup Assistant, and it basically works with the URDF, which is the base representation of a robot in ROS. So you always start with the URDF, and this actually comes straight out of the SwRI ROS package. We just picked up the URDF that SwRI has for these things and integrated it and set up MoveIt with it. The next set of things you can do is specify other things. So in this case, you can say, how does the robot connect to the world? So in this case, this robot is fixed to the world, but you can also have mobile robots. So you can have robots that are either moving in a plane or actually full 6 degrees of freedom as well. And this allows you to specify everything through this GUI interface and be able to plan with this robot. So the other thing that you see the tool doing here is you're clicking through and selecting a bunch of links and saying that those form the right arm or one of the arms of the robot. So if you have a robot with multiple arms, with dual arms, you can plan for a single arm, you can plan for both arms together, and that really is the power of this tool. The next thing that you can do actually is add certain configurations. So typically in robotic applications, if you need some fixed configurations, so the robot needs to be in some fixed configurations like a home position and then a particular manipulation position, you can add all those in using this tool. So what you would typically do with some kind of tablet interface, and basically when you're online, when you're doing your applications or motion planning, you can just refer to these positions directly and say, I want to go back to the home position or to XY position. And essentially, this gives you the advantage of addressing a set of configurations directly by name. And it makes application development pretty easy in that case. Once you go through this whole process, you save a set of generated configuration files. And essentially, you're only going to do this process once per robot. So once you do that, MoveIt is set up for your robot, and you can go ahead and keep working with it. So this is a demo. So we've generated everything. MoveIt is set up, and this is now a demo with the modem and robot. This is, again, in the visualizer, so you can interact directly with the end effector. You can move the end effector around, interact with it. You can specify start and goal state. So in this case, we're specifying a goal state, and we're saying, give us a plan from the initial state to this final position. And you can play back the plans. You can look, you can introspect into them and see how they work before doing anything. So MoveIt really builds on a set of core capabilities, and when you're doing a lot of sensor-based mobile manipulation, collision checking happens to be one of the most important capabilities that you just need to get right. And we have two sets of collision detection implementations right now in MoveIt. The first one is called FCL, the Flexible Collision Library. Basically, it's using high-fidelity mesh models to actually do really precise collision checking for your robots. And the key part is that it integrates real-time sensor data. So you can get real-time sensor data directly in, and it sort of treats it almost natively inside the collision checker. And this is the first time that this kind of capability is actually available, and this makes it really easy for you to start doing collision checking with 3D sensing data. So the other advantage of FCL is it's parallelizable. So this allows you to build applications where you can make things really fast. And you can see for the whole body of the Pier 2, right now we're capable about 2,000 to 3,000 full body collision checks per second. This includes collision checks with the environment. We also have a different collision checker, which is much faster. So this is called the proximity collision detection. It uses a more approximate model of the robot. So this is basically a model with a bunch of spheres. So it lets you do a lot more per second. So you can do 40 to 80,000 collision checks per second, but it's not as accurate as FCL. So the real meat of what you get with MoveIt is an integration with the motion planners. And the way we've designed the architecture, we've tried to make it as flexible as possible. So if you have your own motion planners, if you have your own implementations, it's very easy to integrate them because there is a simple plug-in interface that you can just use. But we provide two sets of motion planners. So one is called OMPL. So this is joint work between Willow Garage and Rice University. So it's a set of randomized motion planners, and this is sort of the bread and butter of the motion planning, a lot of the motion planning that we do currently. We also have the search-based planning library, which is a more deterministic kind of library that can give you more optimal plans. And the cool part is that MoveIt fully integrates these libraries for you with your robot. And everything is automatically configured using the MoveIt Setup Assistant. So out of the box, you can start using these planners with your robot. MoveIt also provides perception capabilities, and again, these are integrated. So you can take any 3D sensor, which gives you point cloud information, and integrate it directly into MoveIt. And over here, what we're showing you is how, with the Pier 2 robot, we integrate the 3D sensor on the robot with the motion planning. So in this case, this is the visualization of what is going on, but in a moment you'll see the simulated view that the robot is seeing. So this is the gazebo simulator, and basically we have sort of a one-to-one connection between the simulator and the real robot. And in this case, what we're doing is adding objects into the world, and in a moment you'll see MoveIt basically integrate these objects into its representation of the environment. And it can use that directly. So you can see that the box, the side of the box that is visible to MoveIt, to the robot, is now visible in the environment representation. And you can take these, so MoveIt can take these into account. So you can do integrated inverse kinematics. So you can see that basically MoveIt told you that that particular configuration was in collision. You can do motion planning, so you can move around the box and you can see the same motion plan executed on the robot as well. So this is a really powerful capability that would be very useful for a lot of applications. And you can see the power of it in this particular demonstration where we're defining a fairly complex scenario for both arms. So this is dual arm planning and execution. So the robot has to move within a fairly constrained area. And you can see that even with two arms and a large number of degrees of freedom, it's able to do pretty well in doing this. And these movies have not been sped up, so these are all 1x, especially the planning parts. We've retained any delays that you see. So these are all, you're seeing things as they're happening. So it's pretty fast for a lot of applications. And one of the key goals we had with MoveIt is to move towards a good software engineering practice where we're doing a lot of testing, where we're doing a lot of comparison and a lot of benchmarking. So when we go out and tell people to use our tools, we can point them back at some kind of benchmarking and test data that shows them how well these things work. So this is benchmarking infrastructure that we developed for MoveIt. Basically, you can put together a bunch of scenes, and I'll show you more examples of this in a second, and specify a bunch of start and goal positions and run a whole set of scenes offline on a cloud or something, and get a bunch of results. And the real key is, so one, it gives you confidence on the numbers that you're getting, and it gives you confidence on the set of capabilities that MoveIt will provide for you. But it's also useful. So there's a lot of motion planners that you can use, and there's a lot of alternate techniques you can use for different components. And what benchmarking will allow you to do is look at your particular application and choose the right component. So if you wanted to choose a motion planner, you could decide based on these results which one is the right one for you. MoveIt can also deal with constraints. So typical constraints are if you're doing a particular manipulation task and you want to keep the object that you're manipulating upright. This is a typical kinematic constraint, and MoveIt can directly deal with constraints like this. There's also other sets of constraints that you can incorporate, and you could even build up some of your own constraints for your particular applications as well. One of the most useful things that we've also been exploring with MoveIt is actually workspace analysis. So imagine a typical industrial job where you need to go in and put a robot to do a particular task, and you have a very approximate idea of what the workspace of the robot is and what the workspace for the job is. So these kinds of tools will let you actually check a lot of these things a priori before you set up all your hardware and figure out what is the right placement for the robot so that it can reach all these positions. So this is essentially a set of reachability checks. So basically you define a bunch of positions, you can run inverse kinematics, and this is all with collisions integrated, and basically figure out where you should put your robot or where your robot should be for these kinds of, for a particular task. And you can also do Cartesian trajectories. So in this case, this is a particular case where we needed to open a door on a small cabinet. And in this for MoveIt, we're specifying the input as a door opening trajectory, and it'll go through, check how the trajectory could happen, come back and tell you what the trajectory is, and at the same time what whether it's actually reachable or not. So these particular tools you could use for things like robot design evaluation. So if you're designing a new robot and you have a particular set of applications in mind, you can run these offline. So you can have, if you want to vary your link lengths, or if you want to change some kind of joint limits, you can have something running offline on a cloud or something and evaluate 100 different designs at the same point. You get back a bunch of statistics on how well each of these designs is doing, and that becomes, that lets you make an informed choice about what you're doing with your designs. The other place, of course, that it's useful is robot workspace placement. So this example of where do I put my robot so it can reach a bunch of locations. And what you're seeing here is in the pictures, these are actually experiments we did with the Pier 2. So the Pier 2 is designed more for domestic environments. So looking at whether it can reach different places and shelves and cabinets. And this graph is actually a comparison of the Pier 2. So the red is the KUKA lightweight arm, and the yellow is the UR5. This is the universal UR5. And this is a bunch of different environments or scenarios with a bunch of different goals, and the robot arms are mounted in a similar way to the Pier 2 on a base, and basically we're looking at how many of these configurations are reachable by one of these arms. And you can see that the Pier 2 doesn't do great actually against some of these industrial arms, especially the UR5 is extremely dexterous in a lot of workspaces. So this is a very informative tool once you decide which robot do I want to use for this particular application? How big should it be? Where should I place it? And going all the way down to how should I design it? You can introspect even into that. So we're here showing you an implementation of MoveIt for a pick and place application. So this is one of the new things in MoveIt that All these things are nice and integrated, and this is an actual implementation running on the robot. So what you're seeing is again real time running on the robot, except that the object is not there currently. But if you worked with our old ARM navigation tools, this is an order of magnitude speed up in the whole task. So MoveIt will do the entire thing for you. It is integrated with object recognition. It is integrated with the 3D sensing, so it'll build the environment representation, it'll compute the grasp for you, it'll figure out the motion plans, and you can actually use it to even control and execute the trajectories on your robots. So it's intended to be a full application set of capabilities that you can use sort of almost out of the box. And another application we're showing, this is with ARM navigation, but we haven't ported this yet to MoveIt, is essentially a web-based interface for interacting directly with the robot. So if you're looking at teleoperation kind of capabilities or applications, this is another set of tools that I'd encourage you to look at as well. So why MoveIt for you? We think MoveIt is the right solution for your ROS industrial applications. So from the transition to ARM navigation, we think that MoveIt could be basically the solution that you use for a lot of your motion, your perception, your grasping and manipulation capabilities, and also complete mobility as well. And why? So from the beginning, when we started looking at MoveIt and started designing it, we looked at doing things the right way in terms of software engineering. So MoveIt gives you very high performance. This has been a key, something that we've emphasized throughout the design process. So ARM navigation used to be a bunch of different capabilities as different ROS nodes. MoveIt is basically, all these capabilities are essentially C++ libraries that you can share and stitch together using ROS. It's got parallelizable collision checking and kinematics, which makes a huge difference once you're starting to do high performance applications. We really care about developers, so we're trying to give developers as much flexibility as we can. So that's why all the core computation is C++ libraries. The communication and configuration happen through ROS. So essentially, if you wanted to, you could take some of these capabilities directly at the C++ level and integrate them directly into your products if you chose to do that. The flexibility is also in adding new components. So for example, if you have, say for the modem in ARM, you have a nice fast IK solver. The current one that we're showing you is basically something that's built to work inside the box. So it's a numerical solver that will work with almost any robot that you can build up. But if you had your own, you can easily wrap it up and incorporate it into MoveIt. MoveIt is designed to be user-friendly. So the idea is you have a new robot, it should be very easy for you to step through and start using it, start using MoveIt with your robot. We've got graphical user interfaces to make it easy for you at the development stage to be able to introspect into it, visualize it, interact with the robots easily. We also have Python bindings, so if you're doing application development and you want to do it in a fast scripting language, you can use our Python bindings and integrate it that way as well. The cool part is the integrated perception, so out of the box it will integrate sensors that give you point clouds as a source of information. We actually have really fast self-filtering implementation, so this is capabilities. So typically when you're doing mobile manipulation or manipulation with manipulators and a 3D sensor in the view, often the ARM itself will occlude the sensors and you have to take the ARM out of your environment representation. And that's actually fairly tricky. We've done it quite a few times. But MoveIt has really fast implementations for that and for the environment representation. And of course, I think this is the real power. You get fully integrated applications. So you get collision-free motion planning and execution. You get pick-and-place applications that you can use almost out of the box. You get these kinematic analysis tools that you can use for different applications as well. And for the future, we're looking to add new features. We're continuously improving MoveIt. We're continuously working on making it easier to use, and we're looking for more use cases. And that's what we're hoping today and tomorrow as part of the Focus Technical Projects, that we can learn more about the ways people will be using this software. And we're going to talk about how you can use this for mobile manipulation tasks as well tomorrow. So if you want to contact us, this is our contact information, and you're welcome to contact us at any point. And if you want to know more about MoveIt, or how you can use it as part of the ROS-Industrial projects, please feel free to let us know.